Here we go. So typically the main defects in terms of post-tensioning structures is to do with the grouting at construction phase. So the aluminium sheaths that house the actual strands themselves, duct will have been poured into the sheaths themselves, and it actually protects these strands from corrosion and also transfers the stresses from the strands themselves to the concrete, and in this case the bridge deck. So when we receive a specification to carry out a PTSI, the client is usually concentrating on critical locations. So I'll just get my laser pointer. So here we've got the midspan of the structure, which is high levels of tensile stress. That's a critical location. You've got sections such as half joints around the piers where the profile of the tendon rises, and due to the construction process of the grout, often at the high points is where you'll find voids within the duct itself due to gravity. If it hasn't been grouted enough, the grout will seep down here, leaving these locations potentially ungrouted and could be corroding inside. So this is a typical specification drawing that we might receive from a client. It's got other testing procedures such as Schmidt hammering, concrete test panels, but in yellow here they've highlighted critical locations. This is two post-tension parapet edge beams and a cable stay structure. So they wanted us to go in and open the ducts up and look inside to actually see the quality of the strands and whether they're grouted or voided. So in the UK, we generally carry out inspections every 3 to 6 years or more if there's known problems with the structure. In terms of post-tensioning, we're looking for defects such as leaking through joints near the anchors, deflection of the bridge, and cracking is quite high on the list, particularly longitudinal cracking. Example on the left here, you can see these red lines were hairline longitudinal cracks on a tunnel that we carried out an investigation on in Ireland. It turned out that after the investigations, these cracks were lining up with the post-tension ducts themselves, but fortunately there wasn't any defects found when we actually opened up the ducts. But the key thing to remember is if an inspector carries out an on-site visual inspection of a post-tension structure, it can often look fine on the outside, but the defects are actually hidden. So you can't tell what's going on inside the duct. So it could get signed off as in perfect condition, but without knowing what's going on inside the PT duct, which is effectively holding that structure up, there's no way of knowing until we've come across some of these newer technologies and ways of determining that. So just to give you an insight into the potential corrosion that can occur inside these ducts, these 3 images were taken after only 6 years of a post-tensioned car park was constructed. So we're looking at close-up views of where we've chiseled out the concrete and exposed the ducts. This is the aluminium sheath, and you can see here we've peeled the sheath back. Top left here is a low risk. So this is what you want to see if you're an asset owner. We peel the sheath back, it's fully grouted, the strands are nice and clean, and that'll be fine for many years to come. And as I say, these are all from the same structure. This was what we class as medium risk, so there's no grout in here. You can actually see the tendons themselves quite clearly. Corrosion process is starting. You can see some corrosion staining, but generally it's still giving the stresses it needs. But this middle image here, this is classed as high risk. So when we actually opened this up, the tendon sheath itself was non-existent. It had completely corroded, and it's exposed heavily corroding tendons. But on the surface, the concrete looked in good condition. So no inspector would have known that this was actually occurring until we actually opened it up. So fortunately, I didn't have a shower this morning when we were opening up this duct, and we got a surprise when about 2 litres of water came out of it. You can see here we've opened the sheath. There was water sitting inside the tendon, which is going to cause heavy corrosion over time. So that's a real bad defect. Here's another endoscope survey that that we carried out 2011 on quite a well-documented structure in the UK. It was Hammersmith flyover. So we're looking here with the endoscope at close-up of the strands. You can see here, this one here is completely snapped, and this one here. And there's a lot of hessian that should have been removed at construction. And the theory was that that was sucking in water to the middle of the tendons, which was inhibitor of the corrosion occurring. There was monitoring systems put on this structure, and evidently it actually ended up having to be closed down. Oh, I've kind of lost where we was. Apologies for that. Just let me get back to where we were. So that structure we were looking at was actually closed down and had to be externally post-tensioned. You can read a good document in the Syria Guide for Hidden Defects in Bridges. So I'm just backtracking here. So in terms of locating the tendon ducts themselves, before GPR and ultrasonics, what we'll get onto, we really didn't have much information other than the as-built drawing. So this is an example of quite a good as-built drawing here. So you can see the tendon profiles, and we had to measure off soffits, off of joints, off of abutments to try and work out exactly where the tendons were and try and find them. And unfortunately, as we all know, the drawings aren't often up to that standard. So here's an example. It must have been scanned multiple times over the years. You can't really work out the numbers very well, and it's hard to see the actual profile of the ducts themselves. So you're really going in blind when trying to locate these ducts. So the only tool we did used to have in our arsenal was a cover meter, which is effectively a metal detector using eddy current technology, very accurate at detecting the first layer of rebar and accurate at determining its cover. But as you can see, the sheaths themselves here are deeper than this first layer, which is always the case. So it will give you it'll give you the rebar pattern of that first layer, but in terms of finding the ducts, it wouldn't really assist at all. So what we had to do, using the as-built drawings and relying on that being constructed to as was supposed to be, we had to carry out a method called stitch drilling. So we'd use a 25mm diameter drill bit and effectively pepper the element with drill holes, and we'd be hitting reinforcement, and then finally we might hit the sheath. And you have to be an experienced operative to know the difference between the rebar and the tendon sheath itself. So it's time consuming. You're adding unnecessary damage to the structure and vibrations to the operatives and time. You can see this is an example here. I'll just explain what we're looking at, this picture on the right. This is where we've excavated out the road surfacing onto the top of a, we've got to the top of the concrete deck. The blue color is the waterproofing. And then we've had to drill a number of holes using the stitch drilling technique. I'd say about 15 holes there till we've actually encountered the duct, and then we've actually overcored it. This picture on the left here is a view down that core hole, and you can see the top of the sheath itself. So, a lot of unnecessary damage to the structure there due to location. So moving on to newer technologies, and this is just primarily locating ducts. Like Tristan and Guido have explained well, we are using GPR, ground penetrating radar technologies, and this is an example of us using Proceq GPR live. So what we've got here, we were scanning a post-tensioned deck. This is a voided cell here, and you've got 6 tendon ducts in the web. They'll be traveling up and down throughout the span, but this is at the pier where they're at their highest. So we've scanned along the road surfacing. You can see the density change picked up by the GPR. This is the top of the road here where my pointer is, and this is the top of the concrete deck. And then clearly, as Tristan was explaining, the hyperbolas show up the actual tendon ducts themselves, so we know where they are. And it's even showed here nice and clearly the bottom of the bridge deck getting thinner towards its edge, as you can see in the drawing here. So it's reducing this damage and need for stitch drilling. And here's a quick example of a scan. This was carried out on a parapet edge beam. So you can use different colors. You can bring the gain in and out. It'll go to about 800 mil. So for our post-tension inspections, that's more than enough. And you can see here, it's picked up the first layer of reinforcement and then really clearly picked up the embedded post-tension ducts. So you've got the ability on the iPad to actually label it up, so it's all ready for a report. And as Guido showed you, I could send it off to my client, or if he was a junior engineer and he wasn't sure, you can send it back to a more experienced engineer in the office just to check that everything's going on right on site. And the great thing about this processing on site is we're often working on motorway closures, on railway. We might only have 3 hours to carry out the work. So it needs to be quick, it needs to be precise. We can chalk it up on site, get our work done very quickly. This is an example of that scan I've just showed you here, and the output with us marking it on the actual surface. So you can see it's very highly densely reinforced. These were actually about 30 mil diameter bars. And you can see in yellow, this is the reinforcement layer. And what we've done in blue is we found the profile of the tendons themselves. And we've been able to overcore the tendons just to open them up and look at their condition. Nice and neat, you know, not many unnecessary drill holes there. We know where we're going in due to GPR. And, you know, we've got all of that done in one shift on a motorway closure. So just to quickly show you how we present some of our results. So picture-wise, we often take a picture of the sheath when we found it. Then we peel the sheath open, and this is one was fully grouted, so you take a picture of that. And then we carefully chisel away to view the condition of the strands and collect some of the grout sample for subsequent laboratory testing. A lot of time and money is spent in getting us to the face of the structure, hiring mutes and closing roads and railways. So we often do a concrete test panel involving half cell, minimum cover, carbonation testing and chlorides, just to get a better feel for the structure. And then just down here, we record the details and locations. So that's explaining how we actually find the ducts. And in the last couple of years, we've been using newer technology in the form of Ultrasonics and the Pundit Live Array Pro, which you can see my colleague is inside a bridge cell using. Now, as explained in previous presentations, the GPR wave won't penetrate into the duct itself. So we can find them, but we still have no idea through NDT the actual condition, if they're voided or not. This is where the Ultrasonics will penetrate through the aluminium sheath and give us a reflection from any voids. So it gives us a locations to home in and do our opening up works. So rather than just having a specification saying open up here, here, and here, we can then trace and scan the tendons and go in at locations we feel there's a higher chance of there being a defect. I'm just going to take you through a project that we've carried out and the processes that I do on site to get the results that we need. So initially, you need to calibrate the gains and calibrate the actual ultrasonic unit. So the way that we do this is we actually GPR to locate the tendons, draw them on chalk, and this was carried out from inside a segmental post-tension bridge. So this is a cell, so we can stand in this section and scan the web here. You've got the tendons in the webs. So what we'll do is offer the Pundit up to the concrete, but off the tendons. So we're doing it below the tendons. And what I'm trying to do, I know there's fresh air here at 500 mil. So I'm just calibrating that to pick up that air as my calibration. So this is the result of that scan. So we're scanning from here. It's the waves are reflecting back off of the air and coming back and giving me a nice reading at, there you go, 490 mil. It does reflect back 43% of steel, I believe. So this is picking up the reinforcement as well. So once we're calibrated, we're then ready to trace the tendons and determine where we think potential defects are. This is a quick video of my colleague carrying out a scan on a post-tensioned beam. So what he's doing here is just tracing along the, sorry, it's a bit blurry, but he's basically tracing along the tendons that we've marked up in chalk. And what we do is we we put a 210 mil mark on the concrete, and that's the width between the transducers. So we're getting a lot of data quickly. I know Guido explained that you can use a stripe scan and AI technologies, which is excellent, but sometimes if we need to get a lot of data quickly, we're doing it just doing it live, and we're getting good results quickly. I'll just take you through this project. So we scanned the tendons here. This is the profile. And then in the first shift, we used the pundit and collected all the data. The next day, I reviewed the data and found that we had 3 different scenarios occurring. So I'm just going to take you through those 3 scenarios. And what we do is, to get real accuracy and confidence in the results, we open up on a number of locations to see repeatability. It gives us more confidence in what we're actually finding. I would never just go off of raw scan data. So this is the first scenario here. So you can see I've upped the gain a bit here. So we're actually picking up the tendon quite clearly. Nothing's really jumping out. This was a typical scan on this structure. And as you can see, we opened it up here at these types of feedbacks a number of times. We're getting a fully gratted tendon. They're slightly corroded, but they probably went in like that at construction, left on site potentially for a couple of weeks. So that was the good scenario. And the bad scenario for the asset owner is when you're seeing tendon ducts like this. So you can see here, these ducts are completely voided. Not any grout has got to them at all. The strands are corroding. And what we were finding was at these instances where these were voided, the actual signal was completely dropping off. So we believe that the signal is getting to that void and it's scattering, so it can't make it to the back wall, it can't make it back to the transducers. So it was just giving us this dark blue reading, which was very consistent each time. And at pretty much all of these locations we opened up, we were finding this type of void. So we were getting good confidence in our results. And the third scenario was we're getting feedback here. So we opened up at this location. Obviously it stood out to us. What we found here was between the actual sheath itself and the face of the concrete, there was some poorly compacted and voided concrete. This has given us these big reflections here, so we knew what was occurring in that scenario. So that's basically me taking you through how we carry out some of our investigations in the UK on post-tension, but it's not just used for that as an application. I'm just going to end with taking you through another example of using the pundit in different scenarios. So our client came to us. They were building a very large warehouse. Concrete slab was 350 mil thick, ground bearing, with a small fabric layer at the bottom. Concrete all looked fine, and then the operatives were drilling holes to bolt in large racking units, and on the odd occasion they were dropping into large voids, which triggered alarms. So from my understanding, a few companies carried out ground penetrating radar surveys, which in a fibre reinforced slab is not worth getting your GPR out the van. It's just going to give reflections back due to the physics and not give you any outputs. So we requested that we carry out a trial on this, and it worked really well. So here you can see on the left, this was where we were finding good quality concrete. So that fabric layer at the base of the slab, so this is the top of the slab here, this is the base of the slab, we were picking it up actually with the ultrasonics and nothing in between. So the signals bouncing back to the transducers from the bottom of the slab with no other voids or defects, and that was good quality concrete. And like I say, to calibrate this, we carried out a number of drill holes just to get confidence in our findings before we didn't need to do that when we were carrying out the rest of the slab. Here we were finding small clumped fibres together, so very small voids, not really massively damaging for the durability of the slab itself, but this is what we were finding in these sections here. So you can still see the back walls giving us a reflection. It's finding its way around these small voids, but then the poor quality voided concrete, this is what we were finding. Like in the PT ducts, the signal's dropping out. It's not getting a reflection off the back wall, so it can't get through the void and it can't get back to the transducers. I'm just going to finish with showing you the picture of where our client cut the slab out to make repairs. And you can see here, this was the voids that we were hitting, and we were getting that output. So very large voids here. We think the fibre was clumping on the actual reinforcement layer, and then not letting the concrete get through. So that could have been very damaging. Saved our client a lot of money, not having to replace the whole slab. We could identify where the problems were, and they could locally repair them. So thank you very much for your attention.